I don't know if I would have given that to him.
All right, let me ask this.
So it only works in one
Is Newtonian
aspect of your.
Go ahead, Jeremy.
John, when we drop something, do we have mass accelerating?
Well, so you want me to answer within Newtonian paradigm or the general
Just
relativistic
in
paradigm?
reality, does
Well, we
mass
don't know.
accelerate when you drop something? Oh, you
We
don't
don't
know?
know we don't know in reality. All I can tell you is what my model says, and then I test it by doing an experiment and seeing if it comes out the way. Now, here's what both general relativity and Newtonian gravity say. If you drop a ball, it will get closer to the surface of the Earth at an accelerating rate.
I'm not talking about Newtonian gravity or Einstein gravity right now. I'm just wondering, in reality, physics. Yeah, all right.
No, it's this Claw the counselor dude that's saying. Can you just mute your mic, please? Claw of the.
Oh, sorry, I'm
whatever his
like bending
name
over
is.
doing something. My bad.
Yeah, just mute your mic, dude.
So you're
Let's
unsure.
let Jeremy and this guy go for a few minutes. No interruptions.
So you're unsure if when we drop something, if mass accelerates. You don't know if that
Well,
happens or not.
yes, it accelerates in the sense that the distance between the mass and the Earth decreases at an accelerating rate. If that's what you mean by acceleration, then yes, both models predict that.
And that's what happens in reality. Mass accelerates when you drop something, right?
No, we can't say that. All we know is that the distance between the two gets smaller at an accelerating rate. That's all we know. General theory of relativity says that the ball is just moving inertially. In Newtonian gravity, the model is that the Earth exerts a force on the ball and then it accelerates because of that force. They both give the same result, but there's a different underlying understanding of why it's doing what it's doing.
Dude, I'm not talking about any of the models or gravity models or none of that. I'm just saying you're unsure if when we drop something, the mass that we dropped is accelerating.
That's right, I am, because all I know for sure is that the distance between the two objects is decreasing at an accelerating rate. I know it's attractive to say that means that the ball really is accelerating, but if you were that ball and you carried an accelerometer, the accelerometer would tell you that you're not accelerating.
So if the mass we drop isn't accelerating, what are the other options? The ground's accelerating up?
Well, that's one option if you want to think of it that way. It is the case in the general theory of relativity that the surface of the ground is accelerating relative to local inertial frames, because local inertial frames in relativity are always free fall frames. So the surface of the Earth is accelerating upward relative to the local inertial frames.
And you said that's what general relativity says?
That's what GR says. That's right.
Yeah, but that's impossible if the globe model's correct, because if you get someone antipodal on either side of the globe and they both drop something, well, we know the radius of Earth isn't changing, so it's got to be the object accelerating down to the ground.
Well, it's just a misunderstanding of general theory of relativity. As I said, general theory of relativity says that the surface of the Earth is accelerating relative to local inertial frames. But the local does a lot of work there, because inertial frames, this is the whole point of relativity, is that because of the curvature of space-time, the local
You gotta forgive him. He's only a
motion
grade
of
school janitor.
inertial frames is different from here than it is in other places.
Okay, so we do know for a fact that the ground and the object are getting closer together at an accelerated rate, so it must be
Right.
one of them or both of them has to be accelerating, correct?
Well, I wouldn't even say that, but I'm willing to kind of, all we know is what I said. That's what we observe. That's all you can.
They
You
teach
have to
this
be
in high
careful in
school?
science
Oh,
to
sorry.
not say more than you know from directly observed fact. And the directly observed fact is that the distance between the two gets smaller at an accelerating rate. If you
Did you
hold
know
an
they-
accelerometer on the surface of the Earth, it will show, your phone will tell you that you're accelerating upward at 9.8 meters per second squared. It'll tell you that.
I know, but we know that's impossible because if Earth is a globe, that absolutely can't be happening because people antipodal would be getting farther away from the center and the globe would be expanding. Now, do you know they teach in
And
high
once-
school? Hold on a second. Do you know they teach in high school in science that when you drop something, it accelerates down at 9.8 meters per second squared? They're teaching that to kids.
Yeah,
And you're saying that's
right.
not
I was taught that. I was
and you're
taught
saying
that.
that's not
Yeah.
and you're saying that's not correct.
No, I'm saying it's an overstatement of what we know. We have to be careful in science to never state as fact things that go beyond what we directly observe. And what we directly observe is the distance between the ball and the Earth. Now, it's very compelling to say that's because the ball is accelerating. And I'm perfectly happy with that. I can work in the Newtonian dynamics paradigm. I can get answers, and we will always. It's a good model. It makes good predictions. But the predictions are based on assumptions about what's really happening that we can never know.
It's not a Newtonian model. I'm talking about just what happens in reality. It doesn't matter if it's Einstein or Newtonian. I'm just talking about the object accelerating down. So let me ask you this: if you don't think it could be, maybe it's not the ball, maybe it's not the ground raising up. Is there like another option if one of the masses isn't accelerating towards the other one? Is there a third option?
Yes, in general theory of relativity, it's the local nature of inertial frames that you're missing. I know it's complicated, it's hard to wrap your mind around, but relativity says that inertial frames on this side of the Earth, inertial frames on this side are accelerating toward the center relative to the ground, and inertial frames on the other side of the Earth are accelerating in exactly the opposite direction relative to the ground there.
Yeah, but if you drop something there and you drop something here, antipodal, they both get closer towards the ground at an accelerated rate. So it can't be the ground moving
That's
up,
right.
So it can't be the ground
And nobody
moving up.
said the ground is moving up.
You said earlier the ground was accelerating up locally.
No, I've said
this
that
guy
if
that keeps
you
signing. Hold on 1 second, John. John, 1 second.
Yeah, okay.
1 second. What's the guy who keeps Cyan's name? What's his name?
What's the guy? Sorry.
Hold on, John.
Oh, sorry. Oh, I thought you were talking.
The guy who keeps Cyan. What does anyone know his screen name?
His name's Claw. Claw, you gotta mute yourself, dude.
Oh shit! My bad.
No, it's
Sorry,
good. I
babe.
got it.
Chill the fuck out, bro.
All right, John, I'm back. So I dropped something here. You're antipodal to me on the globe. You drop something there. It's not the ground accelerating up, right? We can agree on that because the radius would have to get bigger, right?
Yeah, if you want. I mean, once again, I mean, that would be a direct observation that might, in some sense, be difficult to verify. But I agree that the radius of the Earth is not changing.
Okay, so we know that the object has to be getting closer to the ground at an accelerated rate. It's not the ground moving up.
Right. Well,
Right,
we don't
so-
know that, but we know that they're getting closer at an accelerated rate. Yes. And we know that the ground on this side of the Earth maintains a distance of twice the radius of the Earth from the ground on the other side of the Earth.
All right, you have a PhD in physics, and you're unsure if when we drop something that it accelerates down at 9.8 meters per second squared. Is that right?
Well, I'm just trying to be careful. If you mean relative to you standing on the surface, then yes, the answer to your question is yes.
Yes, you don't know what happens when you drop something, or yes, they are accelerating.
No, I can tell you in either paradigm what happens. In the Newtonian paradigm, the ball really does accelerate. In the relativistic paradigm, it simply moves inertially. And the advantage goes to relativity, because if you put an accelerometer on the ball, it will tell you that that ball is not accelerating. If you hold an accelerometer in your hand, it will tell you that you're accelerating upward at 9.8 meters per second squared.
So just to be clear, you're unsure that when we drop something, does physics deal with reality?
Absolutely. When reality collides with our theory, reality wins.
So physics it deals with what happens physically in reality, and you don't know.
Absolutely. It's all about what nature does, and it's never about what nature is.